Welcome to a short presentation and demonstration of ScanCAD International's ScanINSPECT multi-purpose automatic optical inspection and measurement system, a tool that you can use in many different areas of your facility. ScanCAD is a global leader for these multi-purpose inspection, measurement, and data creation systems, with over 1,000 customers in 50 countries using these products over the last 30 years. This presentation will involve a quick company overview, followed by a discussion of inspection and measurement, so we're all clear what we mean when we do 100% inspection. We will then dive into the technology, the hardware and the software that's inside this ScanINSPECT tool. And then finally we'll talk a bit about data creation, the fact that the system can actually create CAD data, hence the name ScanCAD for ScanCAD International. When you leave the presentation, you should understand whether these systems can be of value for you in your facility. For our company overview, just sharing with you here that we have over 1,000 customers installed in those 50 countries, actually for over 30 years now. We've got locations for ScanCAD itself here in the US as well as across Europe. But we do have a global network of distributors and sales representatives that cover the entire world. All of our systems are PC-based, low-cost, and easy to use. They are based on a flatbed scanner imaging system, as you will see in a few minutes. This is one reason why we can keep them low cost and have support in those 50 countries. AOI means automated optical inspection, and we do sell these systems into many different industries: electronics, medical, aerospace, automotive, semiconductor, etc. In many cases, these systems have been sold private labeled under the names such as Siemens, Philips, Panasonic, and some 9 other brand names. These are truly amazing, powerful systems, and they have made sense to be integrated with other people's equipment from time to time. What do we mean by automatic inspection, and what do we mean by measurement? I want to be really clear here. Our system is a 100% inspection system. We're looking at the entire part. We're going to give you a pass or a fail. Is this a good or a bad part? This is very different than measuring possibly 2 or 3 points on the part and assuming the balance of the part is okay. This is not what this system is. Our system is 100% inspection. It is not measuring just a select number of locations. It's literally inspecting millions of features in minutes on a part. Typical inspections are about 5 minutes. Again, this is a low-cost system. We are using CAD data over the image. In some cases, if you wish, you can use Golden Board. Does the system provide measurement capability? Yes. You obviously could do those individual measurements if you want, but the focus is truly 100% inspection. Now, most customers have these existing manual tools and methods in place today, most important being the experienced people that are doing your inspections today. Typically, most companies are manually inspecting parts. What tools do they give those inspectors? Well, in many cases, they'll use a microscope, maybe gauge blocks and pins, rulers, calipers. In some cases, you'll have access to a CMM, a coordinate measurement machine. But the bottom line is these kinds of technologies just are not effective when you're looking at the types of errors that are in today's manufacturing environments. I've got a variety of images I'd like to show you as we move through this today, and we'll also go and actually play with the software itself. On this particular screen, we are looking at an electronics application on the left, which has a solder mask. This is a printed material that is overlaid on a circuit board to prevent solder from shorting between different pins, and it's called solder mask. And this is put on material in a variety of ways, and we can inspect that, and we'll talk more about that in a second. We also can inspect holes. These can be punched, drilled, laser cut, etc. in any kind of material, and we can inspect those holes. We have the lighting, transmissive lighting that push light down through the holes if you wish, etc. Here we have an etch error and a chemical etch process, and finally on the right-hand side, we have the some scratches on a part here, and so we can check for surface defects, scratches, those kinds of things. For right now, why don't we go ahead and let's go into the software for a second and take a look at a part. In fact, this is the part that was in the PowerPoint a second ago, and let's just sort of understand how this process works. First, we import the CAD data. The CAD data is green in color. Next, we scan the part. We typically scan in color. And again, you can zoom in on the part. You can get really close if you want. You can zoom out, whatever you'd like, okay? And you can move up, down, left, and right. Again, this is very easy to use software. I can use the scroll bars here. I can use my mouse, etc. Essentially, what we're going to do here is we're going to overlay the CAD data on the part and perform an inspection. So what I'll do is I'll turn the CAD data on, and we'll go into more detail how that inspection works in the future, but I'll just real quickly perform an inspection just so you can see the errors on this part. If I turn off the CAD data, you can see there's error crosses all over the place here. We turn this off. You can see the error crosses are primarily on the right-hand side. If I turn the color image on and we zoom in, we can put the CAD data on, and you can see the operator is given these error crosses to look at, and they're numbered from 1 to 290, that there is a very serious problem with this part. So you can see that we have some sort of an alignment problem. If we look at the left-hand side of the part, we can see the fiducial is lined up beautifully. If I zoom out and go to the right-hand side of the part and zoom in, we can see that we have a serious alignment issue. And essentially, we're seeing shrinkage in the part as compared to the CAD data. Can we measure that? Absolutely. I mentioned we have measurement capability, so I'll just measure real quickly from here to here, and we can see that there is a 9 mil, at the bottom of the screen here, a 9 mil shift in the X, that the part has shrinkage of 9,000ths of an inch across the entire part. Will this cause problems? Absolutely yes. If you use this green data to manufacture a stencil, to print conductive material onto these gold pads right here, you can see we would have a very serious production problem. And we'll talk more about that in a minute with a Motorola study that was done with this technology. So I just wanted to give you a quick example of what that inspection might look like. There's an alignment error. We also have another error happening here. If I turn this on and off, we can see that we are missing 2 openings completely, which means that not only is there a shift problem with this part, but we also have 2 pads that are, the openings are missing completely. In this case, what we've done is we've been inspecting against the gold pads. So we color separated on the gold pads. We could just as easy inspect the white legend, what we call a silkscreen on this board. We could inspect the perimeter of the board, the cutouts. We can inspect the holes in this board. We can inspect all of the features on this board. It is a truly multi-purpose system. For this particular inspection, we were just inspecting the gold pads on the board. Let me now go back to the PowerPoint presentation, and what we'll do is move to the next slide, which is showing a film inspection. A film inspection. Now, when inspecting photo tools or films, typically we're looking for mouse bites, pinholes, or other kinds of defects. And typically photo tools are used then to add value to future parts. So if the photo tool is damaged, you could be creating some very expensive mistakes down your production process. So let's now take a look at some film inspection examples in these parts. So I'll close this guy out, and we'll bring up our first film example. What's nice about this example here is it permits us to perform an inspection even without CAD data. In this particular case, I'm simply going to inspect this film and look for a defect of a certain size. So I'm going to use this pop-down menu just to show you that we have over 15 different recipes for inspection. The one I used a minute ago on that solder mask, I was using something Gerber comparison check, which is a CAD comparison check. In this particular example, I'm going to use micro defect check, shorts and opens. I'm going to inspect in a window, and we're going to look at defects that are 4 mils or smaller to show me any defects that are 4,000ths of an inch, which would be 100 micron or smaller. It found 13 errors, It numbers them from 1 to 13. It says press N for next, P for previous. So I can go next, 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 or P for previous, previous, previous. It's probably better we get in close and look at it, so I just zoomed in. And by the way, just using my mouse, I can zoom in and I can zoom out, okay? I can also scroll up and down with my mouse, or left and right with my mouse, or use the scroll bars on the screen if you wish. So a really easy to use system. Again, it brought the first error for the operator to look at to say, yes, I do have a problem on the film. Possibly this is something the operator could fix. The next error is a bit more serious. And I'll turn this red area on and off. The red is a guide to help you. That red is that 4 mil tolerance I was talking about, and you can see that we have violated that 4 mil here. This track has gotten too small. It's too small. Same here. Oh, here we have a protrusion. I can turn this on and off, and you can see we use the red for the operator to really help them see what the error is. A protrusion. Here is a mouse bite. Here is a pinhole. Again, I can turn this on and off. Here is a scratch. And another, some sort of damaged part here. Another protrusion, potential short, and another scratch. So you can see that we've gone through the errors on this film. That's just 10 of them. Let's go to the last couple here. And there you have it. So those are the errors on this film. Possibly the operator can fix those or not. The good news is this film should not be placed into production as it is. So you are not adding value that will indeed be wasted in the future. So that is one film example that was not using CAD data. Let me now look at share a film inspection that is using CAD data. So we'll open this up. And what, again, is the same process you saw a minute ago, is that we import the green CAD data, we scan the part in color, and we overlay. So in the process of importing this job right now. So the job is scanned in color, and obviously a film is monochrome anyway. So we'll just color separate on the film. We get this monochrome image. We overlay the CAD data, which is the green data, yes. In fact, if I zoom out, you can even see the targets on the film here, the targets on the film. So if I zoom in a bit, we can see we have the film, we have the actual, the CAD data of the film, we have the actual film. They all are overlaid. And now we'll perform an inspection. Again, I can use my pop-down menu if I want under inspection, okay? Or I can use icons on the left. I'm gonna go ahead and use an icon here and perform an inspection. And here we're looking defects that are 2 mil or larger, 2 mil. That's 50 micron or larger. We'll perform an inspection. Lower left part of the screen is showing the counter running. And what that means is it's comparing the CAD data to the film. And when it's completed, it will show the errors. Here we have 11 errors. So that's error number 1. You can see we have CAD data, but the film, for some reason, if I turn this CAD data off, you can see the film actually has an extra opening in here. Okay, and an extra opening there. There's 3. We have a situation there, another there. And actually, this is a good example of oh, let me zoom in here. Let's go previous on this, high zoom. Here we can see we have a feature that is in the film CAD data, but it is not on the film itself, okay? Okay. So those are the errors that we see that are 2 mils or larger. Now, you'll notice that we had some errors right around the outside of the film, so if I had drawn a smaller window, I could draw a smaller window, and we could, I'll just repeat that inspection again. Okay, again, we inspect in window, 2 mils, and you'll see that you eliminate some of the errors on the border of the film. Again, an area of the film we really don't care about. So we'll reduce the number of errors. So now we only have 4 errors instead of the 16 errors you saw a second ago. Okay, so again, here 1, 2, 3, and 4. Okay, so those are the errors. Now, those are the errors that are 2 mil or larger. Now, let us use the capability you saw a second ago, this micro defect check, where we're going to look for 2 mils or smaller, 50 micron or smaller in that same window, perform the inspection. We have 11 errors. If I high zoom, we can see we can turn off the CAD data now, and we have a small protrusion. Here we have a pinhole. Here we have contamination. I can turn the CAD data back on. We can see we have contamination in between inside an opening here. That's very bad. We have a pinhole here. I'll turn the CAD data off. Another mouse bite, another pinhole, another pinhole. In fact, and I'll just measure this pinhole. Remember, we have measurement capability. I can measure this pinhole, and we can see this pinhole is 0.6 mils, 0.6 mils. This is approximately 13 micron. This is a 13 micron pinhole in the board, okay? And again, there's some other pinholes here. So just showing you the power of the system to use CAD data when CAD data is available, and even when CAD data is not available, you are able to perform amazing inspections with this system. Okay, let's go back to the PowerPoint. And again, that was inspecting photo tools. Photo tools are used in many, many different industries. This is a glass encoder, an optical encoder used to control equipment. And again, the ability to inspect this is critical. And inspecting this manually would be very painful. So again, here we've located some errors, a small protrusion, approximately 25 micron, 1 mil, 1/1000th of an inch. Same here with a bit of a blockage in here. In some cases, the operator might be able to effect a repair on this before the part is shipped. This is actually not a photo tool here. This is the actual part that would ship to the customer, this glass part. This next image shows a variety of other different applications. Here we have printed or dispensed material. This could be epoxy. It could be printed gasket material, for example, a glue. In this case, this is actually printing solder or something called solder paste used for electronics manufacturing. At the bottom, we have a ceramic part with gold material that has been printed or somehow imaged onto the part. And there is a potential short here. There's a 1 mil short for the operator to look at. And then finally, we're inspecting holes over here. What we call apertures or holes. This is for the semiconductor industry, 350,000 apertures. Let's go ahead now and actually play with these parts so you can actually see what these look like in real life. That's what's nice about being on the system, is we can actually look at real customer examples. So let's first look at that wafer from the semiconductor industry. And again, you might be able to equate this to your application area. We don't care if these are holes that have been punched or drilled or laser cut or imaged, or however the holes get there, etched, for example, or even E-form, electroform. Many of these products are electroformed. We will inspect them. And again, it could be medical industry, it could be the textile industry, aerospace, etc. This particular example, again, is the semiconductor business. We start with the green CAD data. We image the part. In this case, using a backlight, we push light through the part, and I'll show you the system in a minute. And then we overlay the two and perform the inspection. I'll use another one of these 15 recipes right here. We'll do this one called small aperture check. And what it's going to do now, lower left corner, it's actually counting down from 340,000 to 0, because there are 342,605 apertures on this stencil. Now the size of these apertures, these openings, are 0.003 of an inch, 75 micron holes. I should share with you that we have customers in the textile industry that are inspecting dye that's used to extrude high temperature, high pressure polymers that make threads. And they are using hole diameters of 0.006 to 0.009 of an inch. And they literally have hundreds of thousands and sometimes millions of apertures in a die. The same system that inspects a wafer stencil for semiconductor will inspect that die for the textile industry, or for oil and gas, or for medical, etc. Now let's look at the first error here. I'll turn off the CAD data so you can see, and you can see we have a complete blockage of that opening. That drill hole is completely blocked. Here we have a partial blockage, a little bit of light getting through, complete blockage, complete, complete, and here we have 2 that are partial. Now what I want to share with you is that this is a good product. This is a good stencil. It happens to be dirty. This stencil passed initial inspection. This stencil was used to print solder or balls onto silicon wafers. And they printed a large number of wafers, and then it was time to clean the stencil. So this stencil went through a cleaning process, and obviously, as you can see, there are blocked apertures throughout the stencil. There are 276 blocked apertures out of 340,000 apertures. Doesn't sound like very many. That's a very low percentage, but believe me, it practically ruins every component, semiconductor component that would be printed using this part. Here's one component that would be good, and it's hard to find another component. Maybe this one here might be good, but the rest of the parts are going to be bad. Maybe this one will be good. So literally you're going to have, if you ran this in production today, you would have a 95% scrap rate on these very expensive components if you did not use the ScanINSPECT system. So this is a real live customer example that I'm giving you. Let's look at a more simple stencil. And again, I'll show you more of the process now. The way the system works is you first import the CAD data in green. You next scan the part, in this case monochrome, using a backlight. And now we overlay. Now I just want to share with you, use these icons here, and this function here automatically flips and rotates to put the CAD data on top of the part. Okay? We then are permitted to be able to perform an inspection. Again, the system compares every aperture here against the CAD data against the part, and it found 57 errors. And again, it numbers them first, second, third. I can zoom in close, maybe zoom out just a little bit, toggle the CAD data on and off, and maybe you can tell me what the error is here. So here we have CAD data, but there's no opening in the stencil. As a matter of fact, we can even see a small opening here, and this was a laser cut stencil. So you can see the laser was cutting, and then something happened. The laser stopped, and the aperture did not drop out. And so both of these apertures are a clear problem. So this is a bad stencil at the very beginning. The next error is an alignment error. This is an example of a possible revision change because you can see that the other features are aligned beautifully, but for some reason, these openings are not in the right position. They're shifted to the right. So indeed, that would be a serious manufacturing problem. I'll skip through this. This is now error number 10. Error number 11 is in this ball grid array, what we call a BGA device in electronics. If we get in close again, we can see here that we have the same kind of problem. If this was a dirty stencil, this could be partially blocked or completely blocked. Or if this was a brand new stencil, we actually have damaged apertures here for whatever reason that aren't properly formed. Okay? So again, just giving you some quick ideas at the bottom of the screen. Yes, we have an alignment situation again. So we can see that, I'll get in close here. You can see that the part is shifted. There's an alignment situation. Okay? So I'll go ahead and escape, close this out. We'll go back to the PowerPoint. And we talked in more detail about this wafer bump stencil and stencils in general. Oh, I meant to also share with you these printed solder paste. Let me go back in and we'll do that real quickly. This is a great application because anytime you have printed or dispensed materials, you can now inspect them. This could be glue, adhesive, epoxy, a printed gasket, for example, or those kinds of things. In this case, we scan the part in color that you see. We then color separate on the part of the part we want to inspect, in this case, this printed material. And now I'm going to draw a window around this area that we want to inspect, and I'll turn on the CAD data, and we'll use yet another inspection recipe. We have all these different inspection recipes. You've seen me use this CAD comparison check. You saw me use the small aperture check and that 340,000 aperture stencil. You saw me use micro defect check, shorts and opens for the films. Now I'm going to use something called aperture area check. Click on this. And what we're going to do here is we're going to inspect in a window. And let's go ahead and flag any errors. Let's say, okay, I want to have fail anything that has less than 50% coverage or more than 125% coverage. I'll inspect in a window, perform the inspection. Okay, bam, we have the errors. I'll turn off the CAD data. I'll even turn off this blue information. And you can see very quickly that this deposit, this printed or dispensed material has more than 50% coverage. This has less than 50% coverage. Okay, so you can see how quickly we can perform an inspection, and try to do that manually with calipers on wet material. This is wet material. Okay, I will quit out of here. Let's go back to the PowerPoint and go to the next slide. What I'm showing you here is an emulsion mesh screen. This is used in many different industries to print materials. It can be used, for example, to print the material you see on windshields, all of those little black dots and things around the edge of a windshield. For automotive applications, this is used here in electronics, and I'll show you an electronic application in a second about this. But it's used, even let's say T-shirts, right? Printing stencils on T-shirts. Possibly you don't need to inspect those, but certainly for high precision applications like cell phones, for example, there's a mask that goes on a cell phone. Instrument panels in aircraft, that kind of thing. So these all can be inspected. In this case, we have emulsion that did not wash out for some reason after the imaging process. It uses a resist. Here we have a pinhole, which is a very bad thing. You'd be printing material where you don't want to. The next sample is showing you wire bonds. The same system that does all the inspections I've just talked about can inspect these little tiny wires, which are 0.7 mil, about 17 micron or so gold wires here. This is the three-dimensional object, so we're actually using focus to focus down into the system. We can inspect the epoxy that was printed. This green material is epoxy underneath this device. Obviously, we just showed you we can inspect the solder paste, which is being used to solder this part on. Underneath the die, this silicon die, there's something called die underfill. That too can be inspected with the ScanINSPECT system. So all kinds of ways you can use this system for inspection. This is the system. This is your first image of the system so far. It is a bench type system, and we'll talk more about that in a minute. Can the system be used for measurement? Absolutely yes. Here's some cross sections here that I'm just showing you where you're measuring the cross section of material and measuring what's going on. So we have customers all over the world using it for that type of application. On the right-hand side, we've been using these terms of thousandths of an inch or mils or micron. I just want to give you an idea of what we're talking about here. A typical human hair has a diameter of 100 microns. So this ring that you see here is the cross section of a human hair. 100 micron, or 4 thousandths of an inch, 3.9 thousandths of an inch, 3.9 mil. Well, I just want to share with you that the errors that we're finding and showing you here, in many cases, are smaller than a red blood cell, which is 7 micron. So the system will scan at very high resolutions and do really high resolution, high accuracy inspections and measurement. So very, very powerful system. Can we work with step etch features in a chem etch environment or in the E-form environment? The answer is absolutely yes. So we can inspect not only the complete cutout of a part, but any kind of logos or features or serial numbers, etc., that are into the etched into the part as well. Here's another part, just another mechanical filter type part. Again, we can inspect to make sure all the hole diameters are the right size and whatnot. What are we saying here? Use this system for first piece inspection, final piece inspection, or even sampling. In many cases, if you're in a high volume operation, you'll want to use this in a statistical process control type environment. So maybe you take sampling of 1 every 10 parts, 1 every 100 parts, etc. For lower volume environments, inspect all the parts. We're giving you full traceability. Every time you perform an inspection, The color image, the CAD data, any errors, hopefully no errors, are all stored in your historical record. So it supports your ISO certification. Again, we can use CAD data or an actual part when we're performing that inspection. Here's an example for some other types of surface defects that we're inspecting for, scratches, those kinds of things. Here's another example of using this in a chem etch environment where we're actually assisting the process of understanding the etch factor. So you can actually use the ScanINSPECT system to inspect parts as they move through the process to verify that you're not over or under etching a part. So you're making sure as you move forward that everything's okay. And if necessary, you can even adjust or improve the photo tool or the data that's making the part to allow for those kinds of situations that are difficult in a chem etch environment. I mentioned a second ago that we inspect the instrument labeling and whatnot and aircraft and those kinds of things. Well, you can inspect characters. Here's a keyboard inspection here. We are used in many different applications in that type of environment. Very important. I mean, I'll use aircraft again. ScanINSPECT systems are being used today to inspect those placards for no smoking, emergency exit signs that are in multiple language, etc. All of that is inspected on a ScanINSPECT system. So yes, applications in aerospace, medical, textile, film, automotive, solar cell, fuel cell, it is a true multi-purpose system. The same system that works in one industry will work in another. In the film industry, for example, Kodak film. Kodak uses this ScanINSPECT system to inspect all film at the time of manufacture, both in the US and in China today. Film is manufactured in 5-kilometer long rolls. The first meter of the film is sliced off and inspected in the last meter of the film. If there are any defects in that type of environment, which is more of a reel-to-reel type environment, those errors tend to go through the entire length of the film. So they will want to catch that, and they can then strip that out at the time of cutting the film to be sold to customers. So it's a very powerful application. Maybe your application is something similar to that. In the photovoltaic environment, there are several processes that ScanCAD systems are used to inspect today. Because again, they are, in most cases, they're printing conductive material onto the photovoltaic polycrystalline or monocrystalline materials. In some cases, they're using lasers to cut holes, and the ScanINSPECT systems inspect the laser. Here's a fuel cell. Again, very important. Any holes in a fuel cell can be disastrous with the hydrogen situation. Here we have extruded materials. This is an aluminum extruded material. We can inspect the die or the finished part, perform all kinds of inspections on that and measurements if desired. That's just a snapshot of measurement inspection. Let's now take a look at the technology itself. This is the bench and this is the scanner. This is the imaging device. Pretend that it's a camera. The bench is an open design that does permit us to inspect those very large and long textile parts, again, up to 5 meters long. The Kodak part is approximately 108 inches by 36 inches, as I recall, and all of that's inspected on this bench type system. The scanner is A3 size, which means you take more than one picture for a large part. The system is aware of the CAD data, so it knows when you're inspecting a large part, you simply move the part, inspect, move the part, inspect, move the part, inspect. The system keeps track of what's been inspected, so you know you inspected the entire large part. Now, the bench can be stand up or sit down. For those large, super large parts, you can add your own benches to the side, so you could feed parts onto this and off one side, and etc. It's a very open architected system. So again, stand up or sit down, adjustable legs, you provide your own PC. We do provide the arms here. The scanner fits underneath. This is a light box. This is providing that transmissive light, or what we call a top light. The bottom light is the reflective light. That's the light from the scanner. So we have both top and bottom lighting, transmissive or reflective. It is a contact system where the part actually lays on the surface of the glass of the scanner. Scanner faces up, the part faces down. If you do have three-dimensional parts or wet parts like I showed you a minute ago, you will use the focus capability of the system. It is calibrated with a glass calibration plate. This is a NIST certified, a National Institute of Standards certified glass plate. The glass plate is stored under the scanner. There's a shelf down here to keep it protected. And then I would like to share with you that you can store those images and data for traceability. Everything that I've shown you can be stored and saved. Again, programming from CAD. Gerber is a form of CAD or golden part. Our objective again is that pass-fail. These are the 7 steps that are typically run today for an inspection. Most inspections, most customers have a 5-minute process. So I wanted to give you a feel for that. So most customers are running with a 5-minute process for inspection. So this is not 5 seconds for inspection. It's not 50 minutes. It's approximately a 5-minute by the time you import the CAD, scan the part, color separate, overlay, inspect, review errors, and then obviously print a certificate or that data is put up in your SPC system. It can be electronic format. When you import the CAD data, by that way, it could be DXF data, for example, or the Gerber data or other formats of CAD data. It again is displayed in green. The part is typically scanned in color. I'm going to show you a short video now. As you will see, we actually are placing a part on the scanner and getting it ready for scanning. So I thought I'd share this video with you. Once the image is scanned, we go through a color separation process where we extract the part of the image we want to inspect. As I shared a minute ago on that circuit board, we could inspect the gold pads or the holes or the white text, etc. It's what you want to inspect, or multiple inspections. There is an overlay process using those icons that overlays the image. I showed you that a minute ago in real time. And then ultimately we get to the inspection. One of those 15 different recipes for inspecting. So here we're doing a Gerber comparison check or the CAD comparison check. And again, this particular inspection, they're looking for errors down to 0.3 mils. That's about 8 microns, so 8 micron errors. Here the errors are marked and they are numbered as you saw, and the operator moves through those errors, seeing if there are any errors, and if there are errors, if they can be repaired. And then finally, we have that reporting document at the end. You could print a paper document that could be sent with the part. For example, if you're shipping this to a customer, an end user, where they actually see that inspection was done, it has a date, a timestamp, when it was last calibrated, the inspection time, etc. Got a few sample images here, but before I do that, let's go ahead and do another real-time example. Let's go to the automotive industry. And we're going to pull an emulsion screen from the automotive industry. Here we go. This particular part, we're going to look for errors that are 1.5 mils or larger. 1.5 mils or larger. That's about 35 micron or larger. We are using the CAD data again on this. The part was scanned in color. Now let me just turn that CAD data back on so you can see it. So the green data on and off. You can see how easy this system is to work. And we now have 21 errors on this part. And if I just zoom in close, hit N for next, you can see where these errors are. So this is the first error that is something very concerning here. And I can put the CAD data back on for you can see that, or even this monochrome image to help you understand where the error is. So you can see we have some emulsion pinhole in here, which would be a very bad error. So you don't want to print that onto this automotive part, which would then get into a car, which could result in a safety issue or a recall. Here we have some contamination, okay, and up here we see another pinhole and another pinhole. So this is giving you an idea of what this looks like and where the errors are. So a very powerful system. Again, I'm not going to go through all the errors, but imagine trying to inspect this yourself. I'm inspecting for errors of 1.5 mil, 35 micron, 1.5 thousandths or larger. And we have the benefit of being able to overlay the CAD data and say, show me any place it doesn't match. Back to the PowerPoint. So in the PowerPoint, I just throw some examples in. This is This can be an etched, milled, or laser cut copper features to CAD data. So here we have imported the CAD, scan whatever it is we're inspecting, overlay, and inspect. Same with this metal stencil. Import the stencil data, scan the stencil, this case in color, color separate, overlay, and inspect. Here we have an example of there's no CAD data needed. We're just simply comparing part to part, a good part versus a bad part, and flagging any errors. Can we do data creation? The answer is absolutely yes. The ScanINSPECT system is able to create CAD data, hence the name of our company, ScanCAD International, scan and make CAD data. So yes, we can make DXF data, Gerber data, etc., or we can modify data. So what I'd like to do here is actually show you an example of that, and this is a published Motorola study. I think I mentioned this a minute ago. By using this ScanINSPECT technology, they are able to reduce solder paste defects by 43%. This is a published study in SMT Magazine, April of 2006. They analyzed 125,000 units over 3 weeks to obtain the data that I'm about to share with you. And here it is. Basically, this is the result of not modifying the CAD data to match the part. On the right-hand side is where we match the CAD data to match the part. So this is an interesting process. Let me go ahead and show you what that looks like in real time. I'm going to go back to that stretched part I saw a minute ago, or showed you a minute ago, the PCB that was stretched. There we go. If I open this up, and we all know that those errors, I'll go ahead and run this inspection one more time just to remind you of all the errors here. Yes? So here's all the errors on this board, and that's very serious. Well, what this represents is this Gerber data, this green CAD data, represents a stencil that's going to print solder paste on this board. What Motorola's study suggested is when you have this situation, we have 125,000 of these boards that we just paid for. The boards are within tolerance. The stencil data, if we cut the stencil, would have a problem. So why not use this technology here called, I'm going to call it here, automatic Gerber rubber overlap. And look what happens. Bam. It overlays exactly. If I get in close now, let's take a look. We now have perfect alignment. Okay, perfect alignment. As a matter of fact, if I run that inspection again, let's see what errors we have now. Guess what? We went from 249 errors, or some huge number of errors, down to just 3 errors. And these are those 3 errors we talked about a minute ago. Remember the solder mask that was missing here and here? These 2 errors. And there's some exposed copper right here that could be a serious problem when printing paste, if they're worried about that, because the solder would actually leak onto here. So they may want to cover this with solder mask. Okay, so anyway, just thought I'd share with you, that is the published study that we're talking about. Let me go ahead and come back into the PowerPoint. And you can see by altering the data, we brought those points in. So we have a really tight stencil which matches the parts, which in the case of Motorola resulted in a 43% reduction in solder paste defects. So essentially, we are creating that digital twin. We are matching the part with its digital twin. Okay, I hope you've enjoyed this presentation. I've been going as fast as I possibly can, giving you as many examples as possible. It's our pleasure to present to you today. Again, we've got thousands of customers. Many of them have a large number of systems installed. For example, one customer in the UK has 26 of the ScanINSPECT systems installed. Again, we are installed in the 50 countries and been doing it for 30 years. This is what we do. So we are proven, we are economical, easy to use, offline, as you can see with our bench, calibrated using our NIST calibration plate, many inputs, many outputs, all that inspection done on a single system, providing that full traceability that many of you need for your ISO compliance and certification, multi-purpose inspection and measurement and data creation all on the same calibrated system. The ability to inspect incredibly small features at very high accuracy, upgradable annual releases of our software for the last 30 years with all kinds of improvements. There are new recipes coming out all the time, new capabilities all the time. And yes, The jobs that ran 30 years ago in 1990 can be run on the system today. In other words, we have maintained forward compatibility. You can open up those old jobs and still open them and see them. Too many companies force you to throw all of your work out. We refuse to do that. We protect your investment. Your data is safe with ScanCAD International. Our objective in the end is to assist you in being green, environmentally friendly with minimizing scrap and rework, eliminating surprises, which means eliminating stress. It's been a pleasure to present to you. Please contact one of our local representatives in your area to see how we can be of benefit to you. We would love to look at your parts and discuss your application in detail. Thank you so much. Take care.